Welcome. I thought we'd begin this lesson with just a little review of inverse relations and functions. So as a reminder, we show an inverse function using the notation f of x with that -1. That means f inverse. A function is inverted by interchanging x and y values, then resolving for y. And inverting a function reflects across the line x equals y or y equals x. All right, so these are some important facts about inverses. And the reason I bring these up is because we're going to learn how to graph the inverse of an exponential function. And the inverse of an exponential function is and it's coming up any moment now, a logarithmic function. All right, so here we have exponential growth in blue. Y equals b to the x. Growth means that the base is greater than 1. And its starting value is 1. So we go through the point 0, 1, because anything to the 0 power is 1. So let's just say, for instance, maybe that base is y equals 3 to the x. Right? Because 3 is greater than 1. Right? Starting value is 1 there. What would be the inverse? Right? We would switch the x and y. Right? So x here is the exponent. I should put it over here. So for an exponential, oops. There we go. So the x is the exponent, and the y is the result. Whatever you get when you raise something, when you raise a given base to that power. Right? And so 3 is our base. For the log function, the inverse of the exponential function, now the y is the exponent. The answer to a log is an exponent. Log looks to solve for the exponent. And x is now the result. What you get when you raise something to a power, some given base to a power. Right? So if an exponential function is y equals 3 to the x, the inverse of that would be y equals log base 3 of x. Right? So y equals 3 to the x and y equals log base 3 of x are inverses of one another. They undo one another. We can also have exponential decay. And here we have exponential decay any moment now. Oh, by the way, notice that the two graphs here, y equals 3 to the x, come on, go back, and y equals log base 3 of the x, are reflections over the line y equals x. Right? So inverses are always reflections over the line y equals x. All right, so now let's look at decay. Again, we have a positive starting value because we're on the positive side. We're above the x-axis. Here we go. So now we have exponential decay, decreases left to right. All right, so let's just say that this particular exponential decay function is y equals 1/3 to the x. Right? So remember, decay has a base between 0 and 1. Right? So let's say it's y equals 1/3 to the x. The inverse would be y equals log base 1/3 to the x. Right? So again, the reflections over the line y equals x, and y equals 1/3 to the x, and y equals log base 1/3 of x are also inverses. Right? And we've already learned how to graph an exponential function. Well, we're going to use what we know about exponential functions to help us graph log functions, because that's going to be an easier way to graph. And so let's learn a few things, and these are in your notes. Characteristics of the graphs of logarithmic functions of the form f of x equals log base b of x. All right, so remember, exponentials and logarithmics are inverses. Right? So if you remember our exponential function, let's go back to 1 on the next page, on the previous page here. So notice exponential functions go through the point 0, 1. Logarithmic functions go through the reverse. They go through the point 1, 0, right? Because remember, x and y are switched between an exponential and a logarithmic, between any pair of inverses. And exponential and logarithmic are inverses of one another. Remember that exponential functions, they have a horizontal asymptote, right? And that was the x-axis, or y equals 0. Well, logarithmic functions, they have a vertical asymptote at x equals 0 because inverses have everything switched. One thing that's not switched is whether it's growth or decay. So just like an exponential function, if the base is between 0 and 1, the function is decreasing. It's going down left to right. And if the base is greater than 1, the function is increasing. It's going up left to right. The graph is smooth and continuous. It has no sharp corners or edges. All right, so at the bottom here we have logarithmic decay. So here is, well, we don't usually refer to it as logarithmic decay, but here's a logarithmic function, and the base is between 0 and 1. And here we have a logarithmic function. And the base is greater than 1, right? Right, so, but for any logarithmic function, the y is going to be our exponent. The base is that subscript, and of course if none is given, we know it's 10. And if we see natural log, we know the base is e. Right? And then x here, that's the result. That's what you get when you raise some base to that exponent. If you remember, exponential functions have a domain of all real numbers and a range from 0 to infinity. Inverses have domain and range switched. So for log functions, the domain is from 0 to infinity, and the range is all real numbers. The range is negative infinity to infinity. Right? So everything about them is switched. And we're going to use that fact to be able to graph logarithmic functions. And actually the steps are pretty straightforward. And if you didn't have any trouble in rewriting a logarithmic function into an exponential function, you won't have any trouble graphing them. So logarithms are nothing more than exponents. We can use the fact that a logarithmic equation is just the inverse of an exponential equation. So graphing logarithmic equations, we're going to rewrite the logarithmic equation as an exponential function. We're going to evaluate the exponential function instead of the logarithmic function because it would be easier. You just have to remember, though, that y is the exponent and x is the result. Right? Because that's how it is on the log, right? Y is the exponent, x is the result. We're going to graph the points and connect to graph our base function. And now in this particular lesson, there won't be any translations or any stretches, but later on we'll be translating our function and maybe stretching our function. All right, so we're going to graph this one, and I think they're all in your notes. All right, so y equals log base 2 of x. To rewrite into exponential form, remember this will be the base. Y is the exponent, and x is the result. So when we rewrite it, we're going to write it just as an exponential. 2 to the y equals x. So we're going to be plugging into y instead of x and and when we evaluate, we'll get x. Right? So that's about the only thing you have to really remember is to rewrite it into exponential form, and remember you're plugging in for y and solving for x, the other way around. Right? So just like before, we'd used numbers like -1. That would be a good one to use. 0, 1, and 2. We could probably use 3 in this particular graph because 2 doesn't grow very fast. right? So this is just like when you were graphing the exponential, except instead of your exponents being the x's, they're now the y's. That's only the real difference, because everything is switched between an inverse, a function and its inverse. All right, so we have 2 to the negative 1, that's just a half. Anything to the 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. Real important, don't forget that these values right here are x values, and the values next to them are y values. So even though we plugged into y, remember that the point is actually this, 1/2 negative 1. Don't get it backwards. And sometimes students just accidentally read it backwards, or they're thinking, you know, that the x has got to be what they plugged in. Not in this case. Right? So these are our points, 1, 0, 2, 1, 4, 2, and 8, 3. Right? So in the x column are the results, and in the y column are the exponents you'd have to raise 2 to get those results. One thing you're going to find about exponential functions, they grow very, very slowly, right? Because the y's are exponents. So my next integer value, if I want to go to 4, my x value would have to go all the way to 16. And the larger the base, the slower they grow, because I'm going to need a bigger and bigger number to get to the next exponent. Because when I raise that base when I raise a larger base to a power, I get a larger answer. So my answers are the x's. All of these graphs are going to have a vertical asymptote of x equals 0, because they're not going to be translated in this particular section. So here is our vertical asymptote, and then let's graph our points, and we're almost done. Yeah, it didn't take very long. All right, so 1/2 negative 1, so right there. And 1, 0. So all of our non-translated graphs, all the base graphs, they're going to go through 1, 0. Unless we multiply by something, they're going to go through 1, 0. And then we have 2, 1, and 4, 2, and 5, 6, 7, 8, 3. Okay? So it takes a really long time for these graphs to grow. The domain, notice we did not cross the y-axis, right? There's no negative x's. So our domain is 0 to infinity. And that's what your domain is going to be unless you translate right or left. The range, however, will be all real numbers because that's your exponents. Your exponents can be anything, right? So the domain is technically the results, all those results that we get. And when we raise bases to powers, we get positive numbers. The range is the exponents. The y is the exponents. And exponents can be absolutely anything at all. All right, and 1 is done. And you're going to find all of the graphs in this particular section are pretty much the same, exact same steps. Because these ones have no transformations at all. So we're starting off easy. Remember, if you don't see a base, if there's no base written, let me write that a little nicer. The base is 10. Right? So if we have y equals log to the x, right? The y is the exponent. Our base is understood to be 10. And the x there is the result. So when we rewrite it into exponential form, we're going to have 10 to the y. So y is the exponent equals x, right? So this is our base, this is the exponent, and this is the result. Just like before, we're going to plug into y and solve for x. But you're going to find that we can't plug in as many numbers, right? Because 10 to a power is a pretty big value, and the x is going to grow really, really fast. But the y is going to grow really, really slow. So 10 to the negative 1, that's 1/10. 10 to the 0, anything to the 0 is 1, and the only other number I can plug in is 10 to the first, and that's 10. If we wanted to, let's say we wanted to go all the way to 2 on y, our x here would have to be 10 squared or 100. So it's going to take a long time before we get to 2. Right? Log functions grow so slowly because their y values are just exponents. Right? So they grow very, very slowly. Again, we're going to have a vertical asymptote right there at x equals 0. Right? And let's graph our 3 points, because there's no way we're getting 102 on there. So the 3 points that we're graphing are 1/10, -1, got to have a negative, 1, 0, and 10, 1. Right, so we have 1/10, that's pretty small. So they're really, really close to that vertical asymptote. And then 1, 0, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, just can squeeze it in. And so there we go. And it is going to keep growing. It's just going to take a long time. Our domain is 0 to infinity. And the range is all real numbers. Right? These graphs are increasing, right, for their whole domain. Right? So if your base is greater than 1, let's add one little thing. Our function is going to increase for the whole domain of that log function. Right? So here our function is increasing. And it's going to be increasing from 0 to infinity, because that's its whole domain. We could do end behavior on this one. The end behavior is kind of interesting. Right? So, and it's kind of interesting because x doesn't go from infinity to negative infinity to infinity. It only goes from 0 to infinity. Right? So our function is going to approach, right? So as I get closer to the smallest value, which is getting closer and closer to 0, our function is going to grow to negative infinity, but not as x grows to negative infinity, as x approaches 0, right? Because that's all x is going to approach. It's never going to be negative. There's just no way you could raise 2 to any power and get something negative. So all your x's are negative, all your x's are positive. They're never negative, right? And then the rest of our end behavior, f of x is going to approach. And as x grows, so will y. Right? Even though it takes an incredible amount of time, our function will approach infinity as x approaches infinity. Right? And actually, we're going to have the exact same description for increasing, decreasing, and the exact same description for end behavior on all these graphs, because A, there's no transformations, and B, so long as they're increasing, right, they're going to be increasing everywhere. Right? If we have decay, then they'll be decreasing everywhere. Right? So let's add that just to help us understand our graphs a little bit better and end behavior. And you can pause if you need to. I'm going to go to the second one we did, this was the first one. And now this is the second one. All right, so again, this is growth because our base is 10 and that's bigger than 1. All right, so it will be increasing on its whole domain, which is 0 to infinity. End behavior, as x gets closer and closer to 0, right, because it can't get lower than 0, your function is going to approach negative infinity, right? It's getting smaller and smaller, right? As the exponent is smaller and small. As the I'm going to need to let me try that again. I'm going to so this way here, how should I put this? This here is our results, right? So as I have smaller and smaller results, right? My exponents, right, are going to be more and more negative, right? Because it's a negative exponent. Right? That's going to make your base the reciprocal and get it to be smaller and smaller and smaller. Right? So f of x is approaching negative infinity. I knew I could get that out as x approaches 0, and your function is going to approach positive infinity as x approaches positive infinity, because it is growth. Right? So you're going to have that same end behavior over and over and over again, right? Unless you move the graph somewhere, or it's decay instead of growth. Let's graph another one. We don't have too many more to graph here before this lesson ends. Now we have a decay. Right? So we have y equals log 1/3 of x, right? Exponential form. Right? This is going to be the base. This is the exponent, because the answer to a log is just an exponent, and this is the result. Right? So we have, in exponential form, we have x equals 1/3 to the y, right? Because the y is the exponent, the 1/3 is the base, and x is the result. Right? So we have, and we'll plug in, we could go all the way to -2, -1. When you're decay, it's easier, smaller negative numbers are a little easier than are your positive numbers. We'll just use 1, right? Because the negative is going to make it the reciprocal. So 1/3 to the -2 power is going to flip it and square it. That's going to be 9. Right? We can graph that. 1/3 to the -1 power is going to be 3, the reciprocal. Anything to the 0 power is 1, and 1/3 to the first power, well, that's just 1/3. So our points that we're graphing, it's actually a good idea to write them like this so you don't accidentally read them backwards. So you don't get confused and accidentally graph them the way you plugged them in, right? Because it's our answer that's going to be first rather than the exponent, what we plugged in. There we go. All right, so vertical asymptote, it's not translated at all, so it's going to be x equals 0. All right, we'll graph our points there, our 4 points. All right, so 9, -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, -2. And then we have 3, -1, and 1, 0, and then 1/3, 1. All right, so now your graph is going to come down instead, right? And you can see that's the pattern. Right? And we're going to have, as the numbers get larger on the x, our y is going to get smaller and smaller, right? Because the more negative my exponent is, the larger my base is, because this is decay. I'm going to be raising 3. Anytime I've got a negative exponent, it's 3 I'm raising to a power. If I have a positive exponent, it's 1/3. Right? So we have domain and range. Again, 0 to infinity on the domain. The range is all real numbers. All right, and let's do our increasing, decreasing, and our end behavior. In this case, we are decreasing everywhere. So if it's growth, right? So if you're, actually an easier way to think of this, if your base is greater than 1, you're going to be increasing from 0 to infinity. If your base is between 0 and 1, you're going to be decreasing from 0 to infinity. Right? So we're decreasing on the whole domain there of 0 to infinity, and that's because this, our base here, can't really think of a log with, I mean you can, but to me it's easier to think of the log as having a base between 0 and 1. Right? And we can do end behavior again. Right? So this time, instead of approaching negative infinity, our graph is approaching positive infinity, right? Because we're decreasing. Right? So the smaller and smaller the x value, right? The larger and larger the exponent is. Because if I raise 1/3 to a larger and larger power, I'm going to get something smaller and smaller and smaller. Right? So our function is going to approach infinity. And if you ever get confused, look at the graph. All right, you can see as x is going to 0, right, your graph is getting bigger and bigger and bigger. Right, so our function approaches infinity as x approaches 0, and the graph is going to approach negative infinity as x approaches positive infinity. And notice, by the way, that this here matches the domain, and this here matches the range, right? And that's what it'll always be that way, no matter what the graph is. All right? Maybe we have one more, or maybe this was the last one. Let's see. Do I have one more? I have one more. Is that the last one after that? And it's an easy graph. Let's just see. Oh, that's the last one. All right, so one more. Let's go through one more. Just one more. Come on back, graph. Come on. We're waiting for you. There we go. All right, so this is the 3 is your base. The y is the exponent on the log, and this is the result. All right, to write it in exponential form, all right, you're going to put the exponent, which is y. You're going to raise your base to that power, and then this is going to be the result. Right? So we're going to plug into y and solve for x. Right? It's a lot easier going that way than plugging in and trying to do it the reverse way. Right? Using the logarithm. It's a lot easier to just keep raising 3 to a power than it is to figure out, okay, what do I have to raise 3 to get that number? That's a lot easier just to raise to a power. All right, so let's use 1. Actually, we'll use -1. Let's go from negatives to positive. -1, 0, 1, and 2. And so we'll have 3 to the -1, that's 1/3. And 3 to the 0 is 1. And 3 to the first, that's just 3. And 3 squared is 9. Okay? So actually, we have the same points as we did before, but they're just reversed. Right? So now it's +2. We're raising and getting, exponent is +2, and that's going to give us 9 rather than -2, and that's because our base is 3, not 1/3. This time we're growth, not decay. All right, so let's graph our points here. We have 1/3, -1, and 1, 0, and 3, 1, and 9, 2. And so we'll graph those. All right, so 1/3, -1's right there, and 3, oops, 1, 0, almost forgot. And 3, 1, and 9, 2. And let's not forget our vertical asymptote right there. All right, I need to get back to the color I was writing in. I don't want to write in yellow, you'll never see it. X equals 0. All right, and then we'll graph. All right, this is growth. So our function is increasing on 0 to infinity. Right? B is greater than 1, and that matches with our domain. Our function will approach -infinity as x approaches 0, and positive infinity, which is infinity, because that's what our range is, -infinity to infinity. There we go. All right, so that's the last one here. Look, I did it in less than a half hour. In the next lesson, all we're going to be doing is taking these graphs and transforming them. Right? And we'll have 2 techniques, one for reflections and stretches, and one for translations. All right? If you have any questions, let me know. Otherwise, bye for now.